Hi everyone, and welcome to this video in which we will be talking about recursion. We will cover what recursion is and why it's useful, and then we will also look at an example of a recursive method call. In order to really benefit from the explanations in this video, a basic understanding of the Java language, in particular knowledge about the memory stack, are required. If you're unfamiliar with the idea of the stack and stack frames, I suggest pausing here and having a look at some resources to get you up to speed. So what exactly is recursion? Recursion is the technique of solving a problem by solving a smaller or simpler instance of the same problem until the problem is so small it can be solved directly. A recursive method, therefore, refers to the process of a method calling different, simpler variations of itself. A real-life example you could think of is the popular Russian doll, where if you take the top off one, there's another doll inside, and inside that one there is another one, until eventually you get to the smallest doll that is the simplest, smallest version of the original doll. Examples of when you might want to use recursion in your code is if you wanted to reorder a list or search through a list for a particular number. A common example of when we might want to use a recursive function is when computing factorials, which will be the basis for our example this video. As a reminder, a factorial is the product of a number and all the numbers below it. For example, 4 factorial would be 24 because 4 times 3 times 2 times 1 is 24. However, writing 4 times 3 times 2 times 1 is actually the same as writing 4 times 3 factorial. But in order to know what 4 times 3 factorial is, we need to know what 3 factorial is, which is also the same as writing 3 times 2 factorial. And in order to know what 3 times 2 factorial is, we need to know what 2 factorial is, and so on. We can see that looking at it this way, each time we try to figure out a factorial equation, we need to know what the result of a slightly smaller factorial is. This essentially describes what we call recursion, being able to split a problem into smaller and smaller versions of the original in order to be able to solve the problem as a whole. Generally, the formula we can use for factorials is n factorial equals n times n minus 1 factorial. So in our example, this would have been 4 factorial is equal to 4 minus 1 factorial, which is 3 factorial. This factorial example is commonly used as it allows us to see how we can handle the need for repetition when constructing solutions in a fairly elegant way. A Java function you might come across that uses this is the merge sort and quicksort algorithms. Let's look at how we might construct a method that can provide us with a way of calculating solutions to factorials recursively, and then we will see exactly how this works. So here we have a method that uses recursion to provide us with a factorial of a number we specify. In order to construct a recursive method like we have done here, there are 3 things that we need to ensure are present. That is, a recursive call, of course, an exit condition to tell our call when to stop, and a way of reducing the complexity of the problem with every call back to the stack, which we do here with the definition that each recursive call should be equal to the value of the previous call minus 1. Now, as we can see, when we test this method out with an input of 5, we get the correct answer of 120. For us to really see how this method call makes use of recursion, we need to understand how this method interacts with the stack, which is the area of memory where our code is executed. So what I'm going to do is place a representation of the stack here. Currently it's empty and contains no stack frames, but what happens every time we make a call to the stack is that a frame is added where the code for that call can be executed. And once that method is complete, that frame is then removed from the stack to free up space. Let's see what we mean by this. So let's take our example where we made the method call using the initial input of 5. Here, we're going to work through this method call so that we can see exactly how recursion works. So at the point that we initially invoke our factorial method, a stack frame is created for that particular call and added to the stack. The code for that method call is then executed. So on the first call of this method, what's happening is that we're going to work our way through the code for this method, which starts off with a check against our exit condition. So we can check, is 5 equal to 1? The answer is no, so we drop down to the else part of our code because the exit condition hasn't been met. Now here, what we need to do in order to compute a result is times n, which at this point is 5, by the factorial of n minus 1, which is 4. So we can see that that's specified right here with another call to the factorial method. This means that we have to repeat this method call using the input of 4 in order to find out what the factorial of 4 is. Because of this, we are now technically in a new method call using the input of 4, and a frame is created for this call and added to the stack. So we can see here that the method is called again with an input of 4. What happens every time we make a recursive call is that the method that made that call becomes suspended until it receives a result from the new call it has just made to itself. So our factorial 5 method is waiting now for us to finish this factorial 4 method and give it the answer so that it can finish running. Now back to this method using the input of 4. So what we do is we check once again if 4 is equal to 1. The answer is no, so we drop down to the else part again. And we see that in order to finish this method and compute a result, we need to find out what 4 times factorial 4 minus 1 or 4 times factorial 3 is. So this results in yet another method call of the factorial method, but using the input of 3, and this is added to the stack. Now in this new method call, we go through our code and do the checks again. Is 3 equal to 1? No, so we drop down to the else part and try and complete this method call. But we see again that we can't unless we make another call to the factorial method to help us figure out what the result of n-1, which for this call is 2, is. So the call of the factorial method using an input of 2 is added to the top of the stack. And the call before it is suspended until we're able to get an answer to this method call we're about to make using the input of 2. This new call, which we've just added to the stack, again goes through the same code as we've had for the other ones, where we check against our exit condition. Is 2 equal to 1? The answer is no. So we drop down to the else part of our statement and see yet again that in order to compute a result, we need to know what the product of 2 and 2 minus 1 factorial or the product of 2 and 1 factorial is. So to find this out, we make what is going to be our final call to the stack using the input of 1. This is because when we now check our input of 1 against our exit condition, we can see that in fact it is met. So we won't be going down to our else part of our statement. Instead, we're told that we need to return the number 1. Now that we've reached a point where we don't need to use recursion, it means that this current method is complete and can be removed from the stack. But now we have the result of this method call, which is 1. The method before that was waiting for this result can be given the information it needs to complete. So this call of factorial 2 knows that factorial 1 is 1. And so can do the equation here of 2 times 1, which is 2, and take that as the answer to this method call. That means this call is complete and is popped off the top of the stack because we now have a value for the result that it was waiting for. Like before, now that that call is complete, the method before it that was waiting on the result of that particular call can resume. So now we know that the answer to 2 factorial, which we were waiting for, is 2. We can complete the result here as being 3 times 2, which is 6. Now this call is completed as we've computed the value of our result. So we move on and see that the call before it that was waiting on the result that we just got can continue with this new information. We have the information that the answer to 3 factorial is 6, and so we can compute the result of this method call and whatever the answer to 3 factorial was, which was 6. So now we can compute the result for this method call of 4 factorial with 4 times 6, which is 24. And like the other method calls, now that we have a result for this call, which is 24, we can remove it from the stack and free up that space. And finally, we arrive back at the very first call that had to wait for all the other calls to finish so that it could get an answer to what 4 factorial is. And since we now know that 4 factorial is 24, it can compute the answer to 5 times 4 factorial. And that gives us a final result of 120. This frame as well is popped off the stack once its method call is complete, and since there's not another method call waiting, we end up back at the place where the call came from, which was our test class, armed with a final answer to use in our print statement. A key thing to mention is that without an exit condition in a recursive call, we risk ending up with an infinite loop which can lead to what's known as a stack overflow and our program crashing, so it's imperative to include one in our recursive method. And so that's how we can use recursion to break down a problem into smaller and smaller pieces and then put all the pieces back together to get a solution. This is not only useful for problem simplification, but can also help us to produce more compact code.